Hello and welcome. Today we are going to be talking about computing intersection multiplicities in Maple with the use of regular chains. So first of all, what is an intersection multiplicity? An intersection multiplicity is a generalization of the notion of a multiplicity of a root of a polynomial. But this time we have more than one polynomial. So it's useful when you have a singular point. It's a tool you would use similar to a tangent cone in the sense that it helps describe the behavior of the singularity. And in particular, it gives us a sense of the complexity of that singularity. So in this case, we have a line and an elliptical curve. We have a transverse intersection and a tangential intersection. The transverse intersection contributes 1, and the tangential intersection contributes 2. And we have an intersection multiplicity of 3. So this is kind of what we will be working with, these numbers here. So let's get into some formal definitions. The first thing we need to talk about is a local ring, and essentially all a local ring is the ring of polynomial fractions that are defined at the point P that we're interested in. And the intersection multiplicity is the dimension as a K-vector space of the local ring when you mod out those polynomials f1 to fn that you're interested in. So how do we compute intersection multiplicities? Well, there's a couple algorithms, and the first one we're going to talk about is the algorithm of Fulton. What he did in the case of two polynomials in two variables is he described 7 rewrite rules that characterize these bivariate intersection multiplicities. So he made an algorithm where you will rewrite the input until you get to smaller, simpler inputs, split, and then compute the sum of smaller computations. And it's a very elegant algorithm. We also have the algorithm proposed by Mora, which is the first algorithm in the general setting solving this problem, and he uses standard bases, and it's implemented in singular. Now, often we may want to compute intersection multiplicities in the general setting without the use of standard bases. And in that case, many of the algorithms seek to utilize some aspect of Fulton's approach. So there's a couple algorithms, and some of them were proposed in CASC 2012 and 2015. And what that algorithm does is it applies a reduction criterion based on tangent cones to reduce the size of the input system from, let's say, n polynomials and n variables to n-1 polynomials and n-1 variables. And if you can continue to apply that and reach the bivariate case, you can then apply Fulton's algorithm and solve the problem. So this was implemented in Maple 2020, and it's under the intersection multiplicity command. But unfortunately, this isn't a complete algorithm because the criterion does not always hold. Recently, a new standard basis-free intersection multiplicity algorithm was investigated in CASC 2021. And this approach, rather than reducing to Fulton's algorithm, tried to extend Fulton's algorithm up. And they did that, but it is a partial algorithm because one of the properties of Fulton does not hold true generically, or one of the things he uses in the algorithm. So now we have two standard basis-free partial algorithms. And what we did is we implemented this new standard basis-free algorithm in Maple, and then we combined it with the old algorithm that was under the intersection multiplicity command to make this hybrid intersection multiplicity algorithm, which applies both of those. Moreover, we also adapted the generalization of Fulton's algorithm to handle points that are not rational. And we also benchmarked this new intersection multiplicity algorithm compared to the one previously in Maple. So that's what we're going to be talking about today. But before we talk about these challenges with the implementation, we first should get a feel for how Fulton's algorithm works, at least in the bivariate setting. So here's those 7 properties I talked about. The first says that the intersection multiplicity will be a non-negative integer as long as your polynomials don't have a common component through the point you're interested in. So it'll be finite, at least in the cases we're interested in. And then we have the next property, which says the polynomials must pass through the point you're trying to study. Otherwise, it's not a root, and the intersection multiplicity is 0. We have the next 2, which basically say we can reorder the polynomials and we can reorder the variables or apply an affine change of coordinates. The 5th one basically you can start to see here how this generalizes the notion of multiplicity. But in this case, we would take the product of the exponents. And 2, 6. This one is one of the more useful ones. This is the splitting property, and this is how Fulton breaks it up into smaller computations. So whenever we have an exact division, you think we can split. And in the 7th property, this is the ideal property, because remember, the intersection multiplicity is the dimension of that local ring after modding out the ideal generated by your polynomials. So as long as we generate the same ideal, then we're going to have the same intersection multiplicity. So we can apply ideal operations like adding a copy of F to G. Here's the bivariate algorithm. So we'll notice, first of all, we assume some arbitrary variable ordering. We also assume the point is the origin, because we can do that by the 3rd property by applying an affine change of coordinates, and we assume it's finite. Then we rule out the case where the intersection multiplicity is 0. We start there, and then we compute the modular degrees, which are basically these things here. We mod out all the variables below x, and then we compute the degree in x. We reorder to assume that one of them will be generically larger than the other. And then we have a condition here stated in terms of modular degrees, but basically it just says y divides f. And when y divides f, we have an exact division, so we can split using that 6th property, the splitting property. And one of these terms we can compute immediately because it's just a multiplicity, and hence the other term will be strictly less than the first one. So we're going to get termination as long as we can get in this yellow case. And the blue case basically says we can always get to that yellow case by performing this syzygy and killing the leading term with respect to the modular degree. So we reduce the modular degree, and this is allowed. We're allowed to rewrite like this by the ideal property, that 7th property. And that's kind of Fulton's algorithm. A couple things I'd like to highlight because it affects what we're going to talk about next is, you see that ordering here, it has nothing to do with the geometry of the actual input system. So we're going to see examples of the generalization of Fulton's algorithm where it succeeds for it succeeds for a good ordering, but fails for a bad ordering. I'd also like to point out that we're assuming it's a point. The point is the origin. And that's going to be a challenge when we try to adapt it to algebraic numbers, when the point may contain algebraic numbers. So I just want to draw your attention to that now before we address those challenges. So how do we get around when the point contains algebraic numbers? Well, first of all, let's describe how that happens. So when you have a polynomial system F with coefficients in a field K, the solution set may lie in field extensions of K. So here's an example where you have the square root of 2 and the square root of 2 plus 1 as a solution. So we're getting these field extensions. Therefore, when we compute the intersection multiplicity, we're going to need to manipulate field extensions. So in practice, field extensions can occur as direct products of fields, and these objects, regular chains, can encode direct products of fields and apply splitting when necessary, like in the case of a zero divisor. And these are implemented in the regular chains library of Maple. Now, as we said, Fulton's algorithm and its generalization assume the point P is the origin. If P is a rational coordinate or has rational coordinates, it's easy to just apply an affine change of coordinates or just adapt Fulton's algorithm slightly to compute this. But when P does not have rational coordinates, then specifying P as a tuple of algebraic numbers presents some challenges. And one natural way to get around this is by encoding the coordinates of P as a solution to a system of polynomial equations. And that's what we do with this notion of a zero-dimensional regular chain, which is a system of polynomial equations. And by adapting Fulton's algorithm to handle a zero-dimensional regular chain as input, then we can compute any solution regardless of if it's in K or in a field extension of K. So that's what we did. And we adapted Fulton's algorithm and its generalization to handle a system of polynomial equations, namely a regular chain, as input. And that's, again, just a triangular system with those algorithmic properties that we want. But because those zero-dimensional regular chains can encode a finite set of points, it may encode more than one point. So instead of returning an intersection multiplicity, we actually have to return a list of points and their corresponding intersection multiplicities in case some of the points encoded have different intersection multiplicities. So that was the first big thing we did. The next one is we benchmark this algorithm relative to the previous standard basis tree algorithm in Maple. So here's our legend for the charts we're about to see. But size, since it's a square system, denotes either the number of variables or number of polynomials. Ordering denotes the arbitrary variable ordering we choose for the first algorithm, the generalization of Fulton's, and a good or bad choice of variable ordering can affect the results. IM refers to the intersection multiplicity. Method 1 will refer to the generalization of Fulton's algorithm. Method 2 will refer to the previous tangent cone algorithm. And time 1 and time 2 are the respective CPU times for both approaches. NA stands for not available and NR stands for no response. So if you didn't get a response in a reasonable amount of time, which I define to be about half an hour to an hour, then we would put NR. So here we have the very first round of tests. These are with our own test cases, not test cases from the literature. And we're only encoding a single point in the regular chain. So it's not a group of points, just one point. The first 8 tests are really simple input systems. It's just a bunch of variables, one of them squared, and for different values of n. So we can see how this algorithm scales, how both algorithms scale. And we'll see the first one runs basically in milliseconds for most of the tests. And then by about n equals 25, we're getting into the second range where it takes about 7 seconds. Whereas when we run the previous algorithm in Maple, right away, we're already taking 3, 9, 22, 45 seconds as the variables get up there. And by the time we get to n equals 25, it takes about 14 minutes. So you get a significant speed up when the size of the input scales. So that's the first observation we make. The next is there's just some general cases that this new algorithm can compute that the old one can't. In particular, test 11 is one that even with the theory, the old one can't compute because the criterion will never apply if you have 3 polynomials that are singular at the point you want to study. But this new algorithm, because it works on different criteria, can apply, and here it does, and it succeeds. And then test 12, we have a slightly more complex input system. So we have 6 variables, but it's not just, the polynomials are not just variables, they're more complex, and it basically accelerates that difference in performance. And you see the second algorithm takes a minute, whereas the first one still just takes 100 milliseconds. So we get some pretty big speed up here. Next, we look at some tests from the literature. You can see they both fail for the first 2. Then we get, we have the first algorithm succeed and the second doesn't for the next test. Then they both succeed, but the new algorithm, the Fulton one, is about a second or 2 faster. Then we get to an input system where the other one is able to succeed for a point, but the generalization of Fulton fails. But if you choose a better variable ordering, then the generalization of Fulton will succeed. And you'll notice, again, there's about a 4-second speed up here. But this kind of motivates why a hybrid algorithm is a good idea, because you can keep both, and that old algorithm can still compute cases, especially if you choose a bad variable ordering. So it's still pretty useful. Lastly, we have a few more examples where they both fail or get no response. And then one more example where the generalization of Fulton's algorithm succeeds, but the old one does not. One more command we benchmarked is called triangularize with multiplicity. And the idea behind this is you don't always know the solutions to your polynomial system before you want the intersection multiplicity. So this says, okay, well, let's just compute the intersection multiplicity at all the solutions. So triangularize gets called, which solves the system, and then intersection multiplicity gets called and computes the intersection multiplicity. Hence why we benchmarked this one, because we changed intersection multiplicity. But because it returns a collection of solutions and their corresponding intersection multiplicities, we define a new metric here, success ratio, which talks about how many intersection multiplicities we computed relative to how many solutions there were. And we'll return that as a fraction. Lastly, because of the implementation of the old algorithm, it returns an error if it can't compute all the intersection multiplicities. So it skews the result a bit in the sense that it only returns errors or full fractions. It won't say we computed one branch, but we can still see the utility here. So Here we have 10 out of 11, 1 out of 2 for that first input system, which we previously failed on. Then the new algorithm is able to compute almost all of the other ones except for the bad ordering until you switch the ordering around. And we get an error for the old algorithm in most of the cases. And then in the ones they do both succeed. Again, we get a 2 to 4 second speed up. And then lastly, you can see, okay, even in some of the examples we failed before, we're now able to compute most of the intersection multiplicities. So 16 out of 17 and 2 out of 2. So those are the results of the benchmarking. And yeah. So in conclusion, what we did is we implemented this generalization of Fulton's algorithm in Maple. And moreover, we combined it with the previous standard basis free algorithm to have a hybrid standard basis free intersection multiplicity algorithm, which applies the generalization of Fulton. And if it fails, we'll apply the old algorithm. We also extended the generalization of Fulton's algorithm to work with zero-dimensional regular chains rather than a point, which allow us to handle algebraic coordinates of our point and work in field extensions. And lastly, we provided benchmarking results to compare the new generalization of Fulton's algorithm relative to the previous tangent cone approach to intersection multiplicity in Maple. And the results suggest that often the new algorithm is going to be faster and can compute more examples. So let's check this out in a Maple worksheet. So we also implemented a calling sequence here where you can not pass a regular chain, just pass in a list of rational coordinates to intersection multiplicity and it can compute it. So here's the most basic case. You have a point with rational coordinates, your list of variables, your polynomial system, and then you call intersection multiplicity, you get 5. If you want to see what it looks like, we can just plot the system here. And it says this system has an intersection multiplicity of 5. Now, as I said, the old criterion doesn't always apply, particularly if all the polynomials are singular. So here's an example where the new approach, which needs different criteria to succeed, is very useful because all of the polynomials here are singular. We have 2 cusps, and then we have kind of a plane that ripples near the origin. So they're all singular at the origin, and there's an intersection multiplicity of 45. And here's some examples with a regular chain. So these are the things we benchmark. So we load regular chains. It's just auto-saving there. We load regular chains. We load algebraic geometry tools. We load chain tools so we can make the regular chain. And then this regular chain encodes not all the solutions to the system, but some of them. So then it computes the intersection multiplicity and says, okay, at these 3 regular chains, we get these 3 different intersection multiplicities for every point in that regular chain. And here are the results. So you can display the regular chains using the display command. And here's what the system looks like. Kind of crazy, lots of points of intersection, but in the 3 we computed, the origin and 2 others, those are the intersection multiplicities. And lastly, let's actually take a look at how the performance compares in practice. So here we have an example. Method equals Fulton will give you just the generalization of Fulton's algorithm, not the hybrid. Similarly, method equals tangent cone will give you just the previous algorithm in Maple. So we can actually see their performance here. So right away, we compute the intersection multiplicity and you display it. And now we try the old algorithm. And it takes about a second or 2. Yeah, so you can already start to see the input or the speed up with even a pretty small system here, but they both get the right result. And then also in some cases, like in this system here, you might not know all the solutions. There's quite a bit of solutions beforehand. So this is a good example where you'd want to try triangularize with multiplicity. And here you see it computes a bunch of regular chains, a bunch of solutions, and we display them and you see, wow, there's quite a few points. And here's the intersection multiplicity for all of those points. And I believe this is the Okaja 2 system, if I'm not mistaken, maybe 3. So that is how this implementation works in practice and some of the different ways you can use it and some of the comparisons. So I hope you enjoyed the presentation. Thank you for coming and have a great day.